Hello everyone, I'm Shruti Kesti. I am working as assistant professor in Department of Computer Science in ABS Engineering College, Ghaziabad. In this video, I'm going to discuss about the minimum spanning tree concept and one of these algorithms to form a minimum spanning tree from the given graph. In this video, we'll discuss about the spanning tree concept, what are the properties of a spanning tree, what are the application of a spanning tree, and how to form a minimum spanning tree from all the given spanning trees, and one of the algorithm, that is Kruskal algorithm, with its complexity analysis. When we are talking about the spanning tree is basically a subset of graph G, which has all the vertices covered with minimum possible number of edges. Hence, a spanning tree does not have any cycle and it cannot be disconnected. This is the basic condition of a spanning tree. First, that the graph should be connected, or you can say by definition, we can draw a conclusion that every connected and undirected graph has at least one spanning tree. A disconnected graph does not have any spanning tree and it cannot be spanned to all the vertices. If particular graph is disconnected graph, then you cannot form spanning tree, because the basic condition of a spanning tree is to go through all the vertices by using the minimum number of edges. And it does not have the cycle. This is the basic definition, or you can say basic condition of a spanning tree. These are some examples. Suppose we have a graph G. Here in this graph, we have three vertices, that is A, B, and C. Just suppose we are naming these edges as 1, number of edges 2, and 3. To make a spanning tree, the basic condition is that you need to connect all the vertices by using the minimum number of edges so that no cycle should be formed. Here in this first example, this is also part of example of a spanning tree. Here we are connecting these three vertices A, B, and C and using edges 1 and 2. This is fulfilling to all the concept. Yes, it's connecting all the vertices and using the minimum number of edges without forming a cycle. If you are considering the second example, again we are connecting all the vertices and using the vertices using the edges 3 and 1 without forming the cycle. And if we are considering the third spanning tree, here you can see that yes, it's also connecting all the vertices but using only true edges, that is 3 and 2. So this is a basic example how to form a spanning tree without connecting, without forming a cycle by using the given graph. If you want to consider that, what is the total number of spanning tree in a given graph? If a graph is complete with n vertices, then number of a spanning tree is n raised to the power n minus 2. If you're taking the last example, in that example, number of vertices is what? 3, n is equals to 3. And we want to calculate total number of spanning trees, n raised to the power n minus 2, or you can say 3 raised to the power 1, that is 3. In last example, you have already seen that for that particular graph, where there are 3 number of vertices and complete graph, we have 3 possible spanning tree. Or you can say in other terms that if a particular graph is containing n number of vertices, then in each spanning tree, the number of edges should be n minus 1. If you want to connect all the vertices or without forming the cycle, this is the basic condition that n minus spanning tree for the n number of vertices. N minus 1 edges are sufficient to form the spanning tree for the n number of vertices. Whether their graph is completely connected, complete graph or not, but number of edges is n minus 1. Now we are talking about some general properties of a spanning tree. We now understand that one graph can have more than one spanning tree. Following are the few properties of spanning tree connected to graph G. A connected graph G can have more than one spanning tree. We have already discussed about that thing. A possible spanning tree of G have the same number of edges and the vertices. Yes, if you are having n number of vertices, then you need n minus 1 edges. That is the basic condition. If you are looking for the last example, we have 3 vertices, and for forming any spanning tree, you are needing 2 edges in all the cases. The spanning tree does not have any cycle. This is the basic property of that spanning tree. And when you are removing any edge from the spanning tree, that graph will be disconnected. It means you can say that in other terms, you can say that a spanning tree is minimally connected. and adding one edge, if you are adding extra one edge in any spanning tree, it will create a cycle, or you can say loop. That is, in other terms, you can also say that spanning tree is maximally acyclic. Some mathematical properties of a spanning tree. Spanning tree has n minus 1 edges, where n is the number of nodes, or you can say vertices. Yes, and for a complete graph, by removing e minus n plus 1 edges, we can construct a spanning tree. Yes, this is also a way you can say. It will also comes to the n minus 1, because in complete graph we have multiple edges from each and every vertex. So in other terms, you can say when you are having a complete graph, and by removing maximum e minus 1 plus n edges, we can construct, or you can say that you can get the number of edges required to form a spanning tree. A complete graph can have n raised to the power n minus 1, n minus 2 number of spanning tree. We have already discussed about that thing. Thus, we can conclude that the spanning tree are a subset of connected graph and disconnected graph. Again, I'm repeating this line. Please remember this one, that disconnected graph do not have any spanning tree. Now, the application of a spanning tree. Spanning tree is basically used to find the minimum path to connect all the nodes in a graph. If you want to connect all the nodes and you want to use minimum weight, minimum load, then you can go for the spanning tree. There are some common application of a spanning tree, that is civil network programming, planning. If you want to plan a particular network, you want to decide a particular network so that you can connect each and every node, then you can also go for the spanning tree. Computer network routing protocol. This is also using the spanning tree concept to get connected with each and every node in the given network. And third is cluster analysis. Now, minimum spanning tree, that is MST. Short form is the MST. Normally, we use this term, minimum spanning tree. In a weighted graph, a minimum spanning tree is a spanning tree that has minimum weight than all the other spanning trees of the same graph. You have already seen that for a single graph, you have n raised to the power n minus 2 spanning tree. Then what is the meaning of this minimum spanning tree? And you can say that the weight of that particular spanning tree should be minimum, so that that particular tree is called MST, or you can say minimum spanning tree. To calculate the minimum cost, to get the minimum cost for a particular network, you can go for the minimum spanning tree. In real world situation, this weight can be measured as distance, congestion, traffic load, or any arbitrary value denoted to the edges. These costs will be covered by using the cost of edges. Let's take an example of minimum spanning tree. Let's understand the minimum spanning tree with the help of this example. Suppose we have this graph here. A, B, C, and D are the vertices, and we have 4 edges which has a weight of 2, 3, 5, and 6. Now we want to form the minimum spanning trees. First, we need to find out how many spanning trees are possible. These 4 are possible spanning trees. First is containing the edge of weight 3, 5, and 6. Second is containing the edges of 2, 3, and 6. Again, these spanning trees are following the basic property of spanning tree, that is all vertices should be covered and no cycle should be there. Second is also using this 2, 3, and 6 edges. Third is using 2, 5, and 6 weight edges. And fourth one is using 2, 3, and 5 edges. In this, if you want to calculate the sum of these cost of the spanning tree, you need to add the cost of each and every edge used in that spanning tree. Suppose we want to, suppose we considering the first example here, we are using the edges of 3, 5, and 6 weight. Just add this one, 3 plus 5 plus 6, that is 40. For second example, the cost is 2 plus 3 plus 6 is equals to 11. In third tree, this cost is 2 plus 6 plus 5, that is 13. And 5, that is 10. So which one is the minimum cost? Yes, fourth one. Fourth one is called minimum spanning tree because it's also following the spanning tree concept, and the cost of this spanning tree is the lowest. So this is the example of your minimum spanning tree. This one is the minimum spanning tree. Now we are talking about the application of minimum spanning tree. already discussed about the spanning tree concept, but when you are considering the cost of that particular network, that tree, then you will go for the minimum spanning tree. Here, minimum spanning tree can be used to design water supply network, telecommunication network, and electrical grid. If you want to form any network for telephone line, for water supply, for electric grid, you want to use the minimum cost for connecting all the nodes. So here, minimum spanning tree is also an example. And even for finding the paths in a given map, you can use the minimum spanning tree concept. Now, we have two algorithms for minimum spanning tree, how to form, or you can say how to form a minimum spanning tree from the given graph. There are two algorithms. First is Kruskal algorithm and second is Prim's algorithm. Both algorithms are the example of greedy algorithm. First, we are discussing in this video, that is Kruskal algorithm. Kruskal algorithm is used to find the minimum spanning tree for a connected weighted graph. The main target of the algorithm is to find the subset of edges by using which we can traverse every vertex of the graph. It follows the greedy approach, that is, choose the local optimum solution for forming the global optimum solution. And this algorithm treats the graph as forest. In every node, it has an individual tree. A tree connects to another only and only if it has least cost among all the available options and does not violate the MST properties. What is MST properties? First property is that do not form a cycle. Cycle is not there in the spanning tree. And if that by drawing that edge, you are violating the property of MST tree, then you cannot add that edge. Now, how does Kruskal algorithms work? In Kruskal algorithm, we start from the edges with the lowest weight and keep adding the edges until the goal is reached. And obviously, if we add that edge only and only if that edge is not violating the property of MST tree. The steps to implement Kruskal algorithm are as follows. First, sort all the edges because we are focusing basically on minimum cost. So, and we are using the greedy algorithm. So in Kruskal algorithm, the first step is that sort all the edges in low high weight to high weight. And now take the edges from low weight and add it to the spanning tree. Only in that case, if that edge to be added create a cycle, then reject that edge. You no need to add that edge if that edge is violating the property of your MST. And continue to add edges until we cover all the vertices, or you can say that until you have draw all the edges, that is equals to number of vertices minus 1, because we all know that the number of edges required to form a minimum spanning tree, or you can say spanning tree for the vertices, is n minus 1, where n is the number of vertices. Here, example of your Kruskal algorithm, just take an example and show how this will go work. Now let's see the working of the Kruskal algorithm. Suppose there is a weighted graph. Here, you need to first step is what? Just sort all the edges in this given graph according to your weight. Now, this is the weight of all the edges. That is, A and B is containing 1 edge, 1 weight, A and C is containing 7, A and D is containing 10 weight, A and E is containing 5 weight, B and C is containing 3, C and D is containing 4, and D is containing is 2. Now you need to sort all the edges according to their weight. This is a sorted weight. Now you need to construct the minimum spanning tree by choosing the minimum. Here you are using the concept of your greedy algorithm. Greedy is what? Local optimum solution. Local optimum is what? Which is the minimum cost, because we are going for the minimum cost solution. So first draw the first edge, that is AB, which is containing the least cost. Just draw this one, and here it's not forming any cycle, then go for the next edge. Next edge is containing the cost of 2, and that is D to E. Now just draw this one again. By drawing this one, you are not violating any property of MST, so you can go for this one. Third one is of B, C, that is containing the cost 3. This one, here again by drawing this edge, you are not violating the property, that is you are not forming any cycle, then go for it. Next edge is what? That is of C to D, that is of 4 weight. Here You can draw this again because it's not forming any cycle. Now, number of vertices. Here you can see that number of edges. Number of edges is what? How many number of edges is there? 1, 2, 3, 4, and 5. 5 vertices are there. So how many edges are required to draw this one? Only 4 edges are required, 5 minus 1. So here you can see that by drawing this last edge, that is C to D, you can get the minimum cost spanning tree. Other than that, no need to add any edges. If you are adding any edge, it will create a cycle. Here you can see that if we are adding the A to E, this will create a cycle. Discard this. If you want to add A to C, again, this is forming a cycle. A to E is forming a cycle. A to C is also forming a cycle. No need to add this one. You can discard these edges. And when you are adding A to D is also forming a cycle. That is what? A, B, C, this one. So discard this one also. And now your final spanning tree is this one. Here you can also see that already we have already tested that. Yes, number of edges, number of vertices are 5. So number of edges what is 5 minus 1, that is 4. So by using the greedy approach of Krishna algorithm, you can form this cycle, you can form this spanning tree with minimum cost. Always this will give you a minimum cost spanning tree. And the cost of this spanning tree is what? That is 1 plus 2 plus 3 plus 4, that is equals to 10. This is the minimum spanning tree. Just we are considering the Kruskal algorithm in terms of pseudocode. Here we are defining that suppose we have a set that is A tends to 5, and for each word we are starting a loop for each vertex, and we are making a set that is V. We are forming a set which is containing all the vertices. Because it's the basic condition Kruskal algorithm, you need to visit each and every vertex only one time. No need to go for that vertex again. Now, sort the edges of E in non-decreasing order. By the way, this is the first step when you are starting your Kruskal algorithm. Sort all the edges in the non-decreasing order. For each edge U to V, take in non-decreasing order by weight and find if set of mu is not equals to find set of V. It means to what? If that particular vertex is not in the set, only in that case you will add the set, because it's the basic condition that every vertex should be visited only once. So in this condition, you are just checking it. If that mu is not equals to V, it is not in the set, then only you will add this edge in the given set and then return the value. If we are considering the complexity of this Kruskal algorithm, this total turning time of the Kruskal algorithm is E log E. And why to say that this E log E? Just considering the concept of this one. This one. First, we know that the sorting is responsible. Sorting algorithm has minimum complexity of N log N. Here we are sorting all the edges. So the sort all the edges, the number of edges is E. So we can say that E log E is the basic complexity to sort this one. This one. This is doing this one, right? And for each edge, so complexity of this one is E log E. And plus, you are checking each and every edge. So you can say you are accessing each and every edge. And you are accessing each and every vertex also. So when you are forming a relation, that you can see that O of E log E. In all these, you will get the maximum limit, that is the upper complexity O of E log Kruskal algorithm. But in Kruskal algorithm, you can also define the complexity in terms of vertices. Here you can see that number of edges will always be less or equal to number of vertices square, because in complete graph itself, it will be forming this condition. So when you are taking this log of each and every side, you can see that log of E is equals to O of log V. Here you can replace this log E by log V to get the complexity in terms of vertices also. So here these two are the complexity of your Kruskal algorithm, that is E log E and E log V. These are the references which I referred for this video, and thank you very much.